Hello, everyone. Hi, Reggie.
Hi.
So welcome to the fourth IMath webinar for this semester. My name is Gino Angelo Velasco from the Institute of Mathematics. So before we begin, let me remind everyone that this webinar is being recorded and is being streamed live on YouTube. The link can be found on the official Facebook page of the UP Diliman Institute of Mathematics. Now also please take note that everyone is on mute by default. So if you have any question, you may raise your hand on Zoom so we can unmute you, or you may type your question in the chat box. Okay, so let us begin. Our speaker for today is Mr. Yuji Sato. He is an instructor in the Institute of Mathematics, and he will be speaking for the differential equations group. So he is currently pursuing his PhD in mathematical sciences in Worcester Polytechnic Institute. So I hope I said that correctly. His research interest is on partial differential equations. And the title of his talk is A Brief Introduction to Stochastic Homogenization. So let us all welcome Mr. Yuji Sato.
Okay. Hi. Hello. Thank you to the Institute of Mathematics for giving me the opportunity to give this talk. Okay, so let me just share my screen so that we can start. Okay, so for today, we'll be looking at stochastic homogenization and in general, sort of look into what homogenization is. Okay, so the goal for today is to have an idea of what homogenization is and the sort of problems that homogenization tries to solve. Also, we're going to be talking about some of the tools and the flavors of the analysis that one would usually encounter in these sorts of problems. Okay, so the format will be we give like a short introduction and look at the periodic case, and then give a short overview as to what stochastic homogenization is, then move on towards looking at qualitative and then quantitative results. Okay, so let's first ask, what is homogenization? Okay, so there are different ways of answering this. Mathematically, when we say homogenization, we want to look at asymptotic behavior of solutions to equations with rapidly oscillating coefficients. But I also find it very enlightening to look at it in a more physical sense. So here we have some examples. Okay, so in the physical sense, what homogenization asks is whether we can observe effective behavior out of things that exhibit a great deal of heterogeneity. So for example, let's look at figure 1. Here we have some kind of a material. So usually people would talk about composite materials. So say in this example, you have some material with different conductivities. Let's say the rectangle one has conductivity K1, the circle one has conductivity K2, and so on. So you have like different material properties. And what that means is that because they have different like conductivities, they would propagate heat differently. So the question now here is, well, will we observe some kind of effective conductivity, some effective behavior if we sort of zoom out and we don't see the heterogeneities anymore, hence the term homogenization. And in this case, we're working with something that has periodic microstructure, and the way that the field developed was people first looked into periodic problems. Then fairly more recently, people have been looking into something with randomness. So here in figure 2, we have something where it could represent some kind of a composite material with fibers that are distributed randomly. So the kind of questions that you ask here is, okay, what would be the effective like mechanical properties of the resulting material? Is it going to be like stronger because of the fibers that you sort of introduce into your medium? So these are the sort of questions that I find to be very motivating for homogenization. So let's see. So let's look at the model problem for the periodic case. So physically, those are the kinds of things that we want to look into. Now, how do those things translate mathematically? So let's look at the at the model problem. So here we have what can be thought of as a steady state diffusion problem. So it can be like a steady state heat transfer problem or mass transfer problem, where the matrix here A, we are assuming that it's bounded and it's periodic, and it can physically pertain to either like a conductivity matrix or a diffusion matrix. And physically, what that means is that it's a way to quantify how your medium propagates either energy or mass. So so this problem, just to make things more concrete, let's look at it as some kind of a steady state heat transfer problem with a source term F and with boundary condition 0. So we just, if you imagine maybe some kind of a plate or something, and you keep the boundary of the plate at a certain temperature, and so, okay, so if A is periodic, then A of this over epsilon for small values of epsilon would be rapidly oscillating. So for example, if you have sine of, let's say, x over 100, the graph of this is going to be like highly oscillating. So the questions that we want to ask is, well, if the coefficient matrix is highly oscillating, what that means is solving for u epsilon, either numerically or solving for it by hand or whatnot, it's going to be very difficult because of the highly oscillatory nature of A. So this leads us to ask whether, okay, do the solutions converge to some other function u0? And does U0 solve some other boundary value problem? So this can also be a motivation of doing homogenization, because given that your coefficient matrix is very oscillatory, solving for U epsilon is going to be difficult. Well, maybe we can solve another problem, which is going to be easier to solve. And and that ties into like, okay, if the solutions to U epsilon would converge to U0, U epsilon is hard to solve. Maybe if the U epsilons are close to U0 anyway, I just solve the problem that U0 solves. And physically, that sort of translates into, well, does the heterogeneous material behave like a homogeneous one, where you don't see these rapid oscillations anymore? And important to ask as well is, how close are U0 and U epsilon to each other? If we want to sort of motivate the problem as, okay, instead of solving a difficult one, let's solve an easier one. So we also want to ask, well, if I'm solving the easier problem, is that close to the problem that I want to solve? Okay. Now, what makes homogenization highly non-trivial? Now, a standard analysis would give you that, so you would have a sequence of solutions indexed by epsilon, and what you would get is that up to a subsequence, you would get different kinds of convergences. So in particular for this one, we'll get something up to a subsequence, something that converges weakly. And because of periodicity, the coefficient matrix would also converge weakly to this thing. And this is the average of A in the unit cell Y. So remember, A is Y periodic. So it's just some subset in Rn. Usually we take it to be like the cube. And this just means we're taking the average of A over the unit cube. Okay, so what we know so far by standard analysis is that you get a subsequence converging weakly, and you get that the coefficients would also converge weakly. However, because we are only dealing with weak convergences, it is not in general true that products of weakly convergent sequences are also going to be weakly convergent. So this convergence is not true. So U0 does not solve an equation where you just replace A with the average of A over the unit cell. And there are examples uh, that you can come up with to see why products of weakly convergent sequences aren't weakly convergent. Okay. So in fact, U0 solves a much more non-trivial problem. So U0 is going to be a solution to an elliptic problem where A0 here is going to be a matrix whose coefficients are given by this complicated looking expression. So we're not going to look into this expression more deeply in this talk, but I just want to say that homogenization is non-trivial because you have to look into products of weakly convergent sequences. And it's not as simple as, okay, they just converge weakly to the product of the weak limits. So here U0 solves a problem with the coefficient matrix given by, so these are the coefficients of that matrix, and chi j here are actually solutions to a unit cell problem. So if you look into the literature, they would say that they are like the first order correctors that you have for the homogenization problem. Now, to carry out these convergences, what people have looked into over the past several decades was, well, we first started with formal slash semi-formal arguments called asymptotic expansions, where we're kind of being very nonchalant about the convergences that we're working with. And this was done in the 60s and earlier. And in fact, it gave us correct expressions for the resulting homogenized matrix. People tried to make that rigorous through Moscow convergence and gamma convergence. This was established in the 60s and 70s. And it involves looking at some kind of a limit, a different notion of limit for functions. Then came two-scale convergence in the late 80s, early 90s, which sort of exploited the periodicity assumption that we're working with. So the sort of techniques before, they stem from convex analysis. So there is sort of room to move into. There is like a bit more information to use, and that is periodicity. And this is what this notion of convergence sort of utilizes. And this was sort of further improved in the early 2000s by Sioranesco and Damlamian and Griso using the periodic unfolding method, which is equivalent to two-scale, but you do the extra work so that you work with things that are easier to handle. So we won't have time to talk about these. There are plenty of papers online that you can consult about these. Okay. Now, with regards to quantitative results, the sort of keywords that you want to look into are like correctors, and these sort of attacks also give you like a theory of correctors. Okay. So that's for the periodic case. So you lean heavily on the periodicity in order to carry out the convergences that you need in order to go from a heterogeneous problem to a homogeneous one. So what do we do in the stochastic case? Okay, so here are going back to our example of like heat transfer. We can think of these things as some kind of material where, for example, in this one here, the black regions would have some conductivity different than the white regions. And you want to ask now, okay, what is going to be the resulting effective conductivity of this material? Like, what will I observe? How would this material behave? Because at the macro scale, I wouldn't see this. I would see something like a grayish sort of material. And it doesn't even have to be as blocky or discrete as this one. We can look into something more smoothened out, like this one, where the different colors can be interpreted as, okay, if we're in this heat transfer example, you also have like different values of conductivity, and then you ask the same questions, like what kind of effective behavior will I observe? So in these examples, you see that there is no periodicity present. So the question now here is, if you don't have periodicity to rely on, what do you do? Okay. So let's talk about a model problem. Let's restrict ourselves to a model problem. So similar to the periodic case, we're looking at an elliptic problem in divergence form. And what that means is the derivatives are, the highest order derivatives are of the form divergence of a function of the gradient of the solution. Okay. So it doesn't have to be that way, and not all elliptic PDEs are going to be in divergence form, but the analysis would be different for things in non-divergence form. So in this talk, we only restrict ourselves to this case. Okay, so we can think of this again as some kind of a steady state heap problem with zero source term and some boundary, some Dirichlet condition. Okay, so you might be wondering, does it have to be zero? It doesn't really have to be zero. You can have a source term and you sort of just tweak the analysis. But to make things simple, we're working in this case. Okay, so here A, instead of being a periodic function, it's going to be a random symmetric matrix satisfying the following matrix inequality. And what this means is that for every vector in Rn, we have the following. So you have the norm squared of a vector v in Rn less than or equal to av dot v less than or equal to lambda v squared. So we just have this. So this part is called ellipticity, and it's an important sort of assumption in elliptic problems. And this gives you boundedness. Okay. So that is the assumption, one of the assumptions for A. Okay, we're not done yet. Okay, so if you don't have periodicity, what do we use? Okay, so before we proceed, let's sort of build the foundation for it. Okay, so let omega be the set of all such matrices A satisfying this. And we endow omega with a suitable family of sigma algebras. So what that means is we're just getting a collection of subsets of omega satisfying some nice properties. And we call that fu. It's indexed by u because A are going to be like functions of positions. These x would be here in u. And u here is a bounded Lipschitz domain. Okay, so we need the sigma algebra because we are going to be focusing on this measure space. So we have a collection of matrices satisfying this. We take the largest sigma algebra, and we assume that we have some kind of a probability measure on it. Okay, so now we have a measure space on these. Okay, so what are the assumptions if we don't have periodicity? What do we use? Okay, so there are two big assumptions that we need. The first one is stationarity, and what that means is that the probability is the probability composed with the translation function. So this, you just translate something here. Z here is an integer tuple. So you just it's literally a translation. The probability is the same. And what that roughly means is that things happening in different meshes are governed by the same random processes. So remember the example that we had earlier with the the random checkerboard. So you can think of it as things in different boxes, they're governed by the same random processes. You don't have something that is Poisson here and something that has a different distribution somewhere else. Another important assumption is we call it the unit range of dependence. And what more precisely, what that means is if you have two sets that are far away from each other, then the sigma algebras are going to be independent. And what that means is that things happening in different meshes are going to be independent of each other. So going back to the random checkerboard example, the different boxes there, what's happening in one box doesn't affect what's happening in another box far away from it. Okay. So they're governed by the same random processes, but they're independent from each other. And we can actually take this assumption in different strengths, depending on what we want to prove. Okay. So let's look at the qualitative results. So it's not exactly qualitative. It's like pseudo-quantitative in the sense that we are going to have control on the difference of solutions between the random problem and the homogeneous problem. But the control that we have is not really quantitative in the truest sense. Like we don't know how fast the error goes to zero. Okay. But moving on, okay, so let's recall that divergence form elliptic PDEs can be recast as minimization problems. Okay, so note that this is only for divergence form elliptic PDEs. Non-divergence form elliptic PDEs, the analysis is very different, but people have looked into stochastic homogenization of these equations. The sort of methods and techniques that I've mentioned before, like asymptotic expansions, two-scale convergence, periodic unfolding, the way that you get the homogenized matrix, which can be thought of as like the effective, like conductivity or diffusivity, the way that you obtain it is by taking limits in the weak formulation. Note that you only have a weak formulation if you're working with a divergence form like elliptic PDE, because to get this, you do an integration by parts, which you cannot do if you don't have this. Okay. But going back, you get the homogenized matrix by taking limits. Now, in this approach, it's going to be different. We are focusing on the problem being a minimization problem. So we are going to work with a sub-additive quantity that we're going to call mu, which is the thing that we want to minimize. And in some ways, it's going to be similar to gamma convergence and MOS convergence because they also sort of work with a similar quantity. So what is this mu? So mu is an infimum of energy. So it kind of looks complicated, but just think of it. If you have a bunch of gradients there, think of it as energy, okay? So you are looking for the sort of least possible energy. So it's an infimum over all possible V in this space. And what that means is that you're just looking for V having some integrability and differentiability properties, but the important part is on the boundary of U, V is equal to this affine function. So it's just this function. Don't quote me on this. I think this is a hyperplane. Well, in one dimension, it's just going to be some kind of a line. Okay. Okay. So that is mu. It's like the minimum energy. And what are the properties of mu? Well, the minimizers of mu are actually the solutions to your elliptic PDE with boundary condition LP. So the elliptic PDE that we had earlier was something like divergence of, my iPad is acting up. You have something like A grad U epsilon equals 0, and you want U epsilon to be equal to LP, where LP here is this function. Okay. So the minimizers of mu are actually the solutions of the PDE that we were talking about, the model PDE that we want to solve. Okay. Now, mu can be interpreted as some kind of energy per unit volume. So this is important. Whenever we want to find information on mu, it's sort of similar to trying to find information on L2 norms of grad V. Okay. And we call that quadratic response. Another important property of this mu is that it is subadditive. And what that means is that if we have an almost every partition of U, and what that sort of means, for those who aren't familiar, you can just think of it as you sort of cut mu into disjoint pieces, and you call those pieces UI. So it's subadditive in the sense that the energy in U is going to be less than or equal to some kind of an average of the energies in the UIs. Okay, so for a function that satisfies this, we call it subadditive. Okay, so recap, minimizers of mu are solutions to a problem. Mu can be interpreted as some kind of energy per unit volume, and mu is subadditive. Okay. Now, so what do we want to solve? What do we want to get? So what we want to get is some kind of a homogenized matrix, which would mean like this random material in the limit approach something that is homogeneous. And that statement translates roughly into finding this homogenized matrix. Okay, so to start, just some housekeeping, we let square M be this cube. It's just a cube. So I have a picture here. D is the dimension. So, oh, wait, I don't have the picture. I'm sorry. I just want to point out that for m greater than equal to n, you can partition this into translates of smaller cubes. And then now I have the picture. So the picture is this. So I hope you pardon my terrible drawing skills. So here we have the dimension is equal to 2, and the green square is going to be square m plus 1, and you can sort of partition it by smaller squares. Here, the smaller central square is square m, and these are just translates of that. So that is what I'm saying here. So we're working with triadic decompositions. Usually people in harmonic analysis would be looking at dyadic compositions, very natural. But now in our case, we'll be looking at triadic decompositions, okay, because so looking at this example, it gives you cubes that don't touch each other. So it's a matter of convenience. So for example, this does not touch this. And remember our independence assumption from earlier. So that we can utilize that, we're dividing into into these triadic cubes. Okay, so let's go back. So the goal is to find this A bar. So how do we find this A bar? We are going to use subadditivity and stationarity to show that we have monotonicity, that the expectation of the energy at a larger square, at a larger scale, is going to be at most the energy, expectation of the energy at the smaller scale, okay? So how do we show this? Well, we know that we can partition this larger cube into translates of this, so we're going to use subadditivity. So you partition this into translate of that, you subadditivity, what do you get? The energy at the larger scale is at most an average of the energies of these things in the smaller scale. Now, when you take expectation, because of stationarity, note that things in different meshes are governed by the same random processes. Hence, the expectation of the energy at the translate of a cube is the same as the expectation of the central cube. So you do some bit of algebra, you get this. Okay. So now we have this. And note as well that mu is bounded. So you have monotonicity and boundedness. And that gives you that we can define the limit of these expectations, and we call that mu bar of P. And in fact, because of monotonicity, the limit is going to be the infimum of these quantities. So this limit is going to be well defined. Now, as it turns out, mu is going to be a quadratic form, and hence it would define now a deterministic positive definite matrix A bar, and this A bar is what we call the homogenized matrix. So the way that we're doing this is very, very different from, for example, like standard books on periodic homogenization, where they look at limits of the variational form of the problem. So here it's sort of a bit different. Okay. So now that we have this, the next questions that we want to ask is, okay, what kind of solutions do we have for a problem with A bar as a coefficient matrix, and how close are those solutions to the solutions to the random problem? Okay. So to help us answer that question, let's introduce this modulus. So it's just a supremum of this quantity. So what it means is that omega can be thought of as some kind of modulus that measures the uniform convergence, uniform in the sense because it's a supremum, the uniform convergence of the energies at scale n to this limit sort of energy. Note that by monotonicity, we know that omega n actually goes to 0 as n goes to infinity. However, okay, first I want to point out that we're introducing this quantity because, again, what do we want to show? That the solutions to the random problem converge to the solutions to a homogenized problem. So we want to ask, well, how fast is that convergence? So we are introducing this quantity because our analysis would show that the control on the error, that difference between random and homogenized, is going to be controlled by this quantity omega. However, there is a problem. Since since the definition of mu bar came from a monotonicity argument, we have that it's monotone, it's bounded, hence we get that the limit exists. There is no information on how fast the convergence is. So even though our analysis would be in terms of this omega, which we know would go to zero, and kind of has like a quantitative flavor, it's not a true quantitative result because we do not know how fast this goes to zero. Okay. So yes, it's only pseudo-quantitative because they depend on omega and it doesn't converge to zero. Okay. So the first convergence result is the expectation of these quantities are controlled by something which goes to zero as m goes to infinity, and we know how fast. This is like deterministic. This is also deterministic. These are expectations, but we don't know how fast this goes to zero. Okay. Now, what is this? This is a matrix defined by the quadratic form mu. So mu, the energy is actually for fixed m. This is going to be a quadratic form in P, and that would define this matrix A. Okay, so we're not going to prove this or sketch the proof, but we're just saying that at this point, we can control this by something which we know how fast it goes to zero, and something that we know will go to zero, but we don't know how fast. Okay. So those are for this. What I want is I want convergence of the solution, the solution to the random problem to the homogenized one. So to help us with that, we introduce these quantities. So first, curly EM. It looks complicated, but the only thing that you need from it is that it monitors the convergence in smaller scales n in M. So it kind of looks complicated because of all the other terms, but it's just an average of these error terms. So you can think of it as average of error terms in smaller scales n than M. Okay. We now introduce here this function phi. And for those familiar with homogenization theory, so it's going to look like what is called a corrector. So V here is the solution to the boundary value problem in this square with this boundary condition. So E is just a vector in Rn. So we're defining phi to be the solution in that square with E as a boundary value, as a boundary condition, minus this sort of affine function. And this is some kind of a naive form of a corrector. And why this is so, why not use more sophisticated correctors like in the periodic case for those familiar with homogenization? We can answer that in the question portion of this talk. Yes. Okay. Okay, so we introduced curly E of M. We introduced this function that we're going to use. And now let's introduce curly E prime of epsilon. Okay, so the way that epsilon and M is related is just through this. So as epsilon goes to zero, M goes to infinity and vice versa. So what is this complicated looking expression? Okay, so let's break it apart. So this quantity measures, okay, so the first one measures how flat the minimizers are. So V is a minimizer. This is flat because it's affine. So it's just going to be some kind of a plane. So the first quantity measures how big this function is. And this is going to be small if V is close to this flat thing. Hence, we say that the first term measures how flat the minimizers are. The second term measures the convergence of the fluxes. So the matrix times this is going to be some kind of term corresponding to fluxes. So this just sort of quantifies the convergence of the fluxes. Okay. Okay, so we have these things, okay? Now, one can show that curly E prime of epsilon can be controlled by epsilon and curly E of M. Okay. And that curly E of M, let's look back at curly E of M. So curly E of M is just an average quantity of the error terms. And we know that the expectation of the error terms would go to 0. So doing the calculations, one can show that the expectation of curly E of M is controlled by a quantity that you know would go to 0, and you know how fast it would go to 0, and something that would go to 0, but you don't know how fast. Okay. So the point here is that the expectation of this quantity is controlled by something that would go to 0 as epsilon goes to 0. Note that as epsilon goes to 0, and m would go to infinity. Okay. Okay, so yeah, that is what that is what we said. Okay. So what is the result, the homogenization result for the Dirichlet problem? Okay, so there will be a bunch of details, but let's just focus on the essence of this result. So we have the random problem and we have the homogenized problem. So the question we want to ask is, how close is U epsilon to U? And one can show that the error terms, which measures how close U epsilon is to U, is controlled by data in a quantity such that when you take its expectation would converge to 0. So if you take the expectation of everything, this term would go to 0. Okay, so you have actually L1 convergence, and that means that up to a subsequence, you get convergence of these terms for almost surely A. Note that A is a random matrix, so for almost surely A, you have that they would go to 0. Okay, but the question still stands that we don't know how fast they would go to 0. Okay, so we're going to look into that in a bit, but first let's sort of sketch like what are the tools that we need in order to obtain a result like this one. So some technical tools is you would think that in these problems, it would rely heavily on probability theory. But the thing is, you just sort of fix the random variable A and do the usual, use the usual tools that you see in PDE theory and analysis. So for example, it would be very helpful to sort of separate or sort of partition your domain into something which is strictly inside, compactly contained inside, and the boundary layer. So here, the pink one is the boundary layer. I sort of drawn it thickly so that it's going to be more evident, but in reality, this pink region is going to be thinner. So now what you want to do is to estimate a bunch of error terms here and error terms here. And to do that, you have two things that you can use. One is standard de Giorgi-Moser estimates, which looks into estimates inside. And in fact, because you're inside, it's very nice. It gives you something very strong in the sense that you have control on the L infinity norm of your derivatives. And this is much better than LP norms of your derivatives. On the boundary, it's going to be just a little bit worse. We have Mayer's estimate, and what that means is that we don't have L infinity. We get a little gain in integrability. So a priori, you have that the gradients are going to be in L2. In fact, by Mayer's estimate, we have that you have a little bit of gain. You have a little bit of higher integrability. And that is going to be enough using standard arguments to estimate derivative terms on the boundary layer. Okay. Another technical tool is going to be the multi-scale Poincare inequality. And to save time, let's sort of quickly go through it. So the classical one says that you can control L2 norms by the gradient. Multiplied by this factor, where this sort of this is proportional to the volume of this domain. So this is sharp. However, since we're working with something where it's homogenization, you expect some kind of canceling out as you look into larger and larger scales as things become finer and finer and you don't see the heterogeneities anymore. You can leverage that. You can leverage canceling out in larger scales in order to get something that is better than this. So although this is a bit complicated looking, in a lot of situations, this term is actually going to be smaller than this because so you still have grad u, but the other terms, if your function cancels out in larger scales, then you have that these are going to be small, the averages are going to be small, and their contribution is just 3 to the n compared to this big 3 to the m. So for like large values of m, that gives you some kind of an advantage. So classical Poincare is the sharp thing, and what that means is you want control on L2 norms by gradient, by the gradient of your function. And what we're saying is that in the problems that we're working on, you can leverage out, canceling out of functions you're working with in larger and larger scales to get something better. So these are just some of the tools that you need in order to prove the result that I've shown you maybe like a couple slides ago. Okay. So those are the tools. But the question is, well, how do you get the result? So what you use is called the oscillating test function method. And for those familiar with homogenization theory, this is very similar to Tartar's method of oscillating test functions. So you use a special test function. So since we're working with a divergence form elliptic PDE problem, you have a weak form. And that weak form, it needs what is called a test function that you sort of plug into the equation. So in this method, we're using a specific kind of test function, which is W epsilon, where it's equal to this sort of complicated looking expression where phi here are the correctors that we have from earlier. Remember that measuring norms of phi sort of measures how close the minimizers are to a flat function times the derivatives of u. Okay, eta here is going to be a cutoff function, and it's going to be 0 in the boundary layer. This is standard in a lot of things that you see in PDE theory. Now, W epsilon can be thought of as some kind of a primitive 2-scale expansion of U. 2-scale in the sense that you have one scale, which is macroscopic X, and another scale that sort of looks more into the heterogeneity of your problem, this X over epsilon. Remember, in the periodic case, the terms with X over epsilon, those sort of introduce the rapidly oscillating behavior that you would see. Okay, so this is some kind of a primitive 2-scale expansion of U. And the idea is, if I want to measure the difference, the distance between U epsilon and U, it's just going to be some kind of a triangle inequality thing, where I measure the distance between U epsilon and this test function, and W epsilon minus U. Okay, so the way to estimate this, you use this as a test function. There are plenty of technical details, but the essence is you use this as a test function and estimate the remaining terms with something like this. And for the other one, note that W epsilon minus U, so move this to the other side, it would be just a bunch of these terms. So the estimates on this would just be dependent on estimates on the gradient of U plus the corrector terms, okay? So with those tools, you can get the result that we had before, but note that it's not a true quantitative result because the controls that you have, you don't know how fast they go to 0. So the question now here is, how do we make it quantitative? And in fact, these results were only discovered fairly recently. So in math and in analysis, a lot of times when you want to overcome some kind of difficulty, there is some kind of price to pay. You need some information that would match the problem, the difficulty that you need, that you're facing, that you want to solve. And in this case, as it turns out, looking at the Neumann problem is going to be helpful. So the Neumann problem is the same sort of problem, just with a different boundary condition. So instead of prescribing the value of u on the boundary, we're prescribing the flux. So similar to the Dirichlet problem, one can show that solutions to the Neumann problem are actually maximizers of some function that can be thought of as energy. So we're calling this the maximum energy mu star. Now, mu star is going to be a quadratic form in Q. Hence, it would define this matrix, which we're calling A inverse of A inverse star. And one can show that the minimum energy in the Dirichlet problem plus the maximum energy in the Neumann problem is greater than or equal to P dot Q for all P and Q. And for those working in convex analysis, this is sort of suggesting that maybe mu and mu star are conjugate functions of each other. And hence the Neumann problem and the Dirichlet problem are dual problems to each other. And in fact, that is what we're going to use, okay? So to get a control on the error, we're going to rely on how fast can we make these problems dual problems to each other. So to help us with that, let's introduce this function j, which is just mu plus mu star minus p dot q. And what this measures is that it measures the defect in convex duality between mu and mu star. So it measures how close we are to the Dirichlet and the Neumann problems to being dual problems to each other. So properties of J, we have first, we have similar properties that we have seen from mu. We have that you can interpret this as some kind of energy and so. And we also have the J is subadditive, similar to how mu was subadditive. Okay. So recall that what we only know so far is the expectation of the error is controlled by a quantity that goes to zero as epsilon goes to zero. We do not know how fast this term goes to zero. So the additional information that we need is that in larger scales, the Neumann and Dirichlet problems are close to being dual problems to each other. And what that translates into is that J would converge to zero in larger and larger scales. So this is exactly the information that we need to get the quantitative information that we're looking for, that the error is going to be controlled by J. Okay. So the convergence result that we need is something like this. You can think of it as these are just error terms. It's controlled by we're going to explain the notation in a bit, but you can think of this as the error is controlled by two things, one that is deterministic and one that is random. Okay, so now let's talk about like what does this notation mean. So given a random variable x and some numbers s and theta, we say that x is less than or equal to curly O of s of theta if the following holds. Okay. And what this means is we have control on tail behavior. So to see that by Chebyshev's theorem, we have that if this is true, then the probability that x is bigger than this, so this is the tail of x, is going to be less than or equal to something that is exponential in t. So for big values of t, the probability is small. So what we actually have here is that the tail behavior of this minus this thing is exponential, and that goes to zero exponentially as n goes to infinity. Okay. So I would also like to point out that similar to the qualitative case, once you have control on this, then you have control on the errors, like how close u epsilon is to u. Okay, so the question here is, how do we prove this? Now, the key steps would be, okay, the errors are controlled by J. And you can show this just by the definition of J, the definition of these terms. So these are fairly straightforward to show. And actually, this is a really like key step, because without the dual problem, we don't know how fast this goes to zero. But with the dual problem, we are leveraging that. Okay, I have a control on how small these quantities are, provided that I can control how fast the Neumann and the Dirichlet problems are close to being dual to each other. Okay. So that is like the missing ingredient that gave us what we need. That's the price to pay. Looking at the duality between those problems. The next key step is that this is where we use probability theory. So because J is subadditive and bounded, we actually have the following concentration inequality. And this uses the independence assumption strongly. So we really need the independence assumption that we talked about at the start of the talk in its strongest form to get this. So what this means is that we have a control on the tail behavior of J minus its average. That is just going to be big. The probability that that's going to be big is controlled by an exponential function that goes to zero as you go into larger and larger scales. Another way of interpreting this is that J is controlled by some this fixed quantity, deterministic quantity, and a random thing. Okay. Lastly, this is in fact the most non-trivial to prove of the three, is controlling the expectation of J. So we have that we can control uniformly the expectation of J, and it's nice that you only need to use the independence assumption in a weak manner in order to show this. And the control that we have is more precise in the sense that we know that it's controlled by a quantity that would go to zero, but we know how fast it would go to zero. So how do these things help us to get what we want? So note that we want to control this. So the first step says that this is controlled by J. Second step says that J is controlled by these. So we just need to control this. The third step gives us that control. Okay. So let's see. Okay, we have a little bit of time. So how do we get the third step? That's actually the most non-trivial part to show. And one can do that if you can show that the expectation of J would contract uniformly. And what that means is that as you go into higher and higher scales, the following would hold. For some fixed theta, which is independent of n. So if you show this, then you're going to be good. You just sort of iterate this until you get to the zeroth scale. Okay. However, that is not true. It's not that it's not true. This is too strong and hard to prove. So what we have instead is that the estimate of J, which can be thought of as estimate of the energy, is controlled by something which we know would go to zero, plus a bunch of terms, which we called a scaled additivity defect. And what that means is that this measures how strict the subadditivity is between scale n and scale like n plus 1, between adjacent scales. So control on this is given by something that we know how fast will go to zero, plus a bunch of terms happening at scales smaller than n. Okay. So to do that, we first note that J is comparable with the energy. Okay, so this is quadratic response that we had earlier. And what that means is estimate on J, so expectation of J is controlled by expectation of energy. Remember when we said that gradient terms, L2 norm of gradient terms can be thought of as energy, plus some defect terms. Okay, so now the question is, how do we control this? And that would come from the Caccioppoli inequality, which is a standard of PDE theory, whereas we use information from the equation. So because of the fact that V would satisfy some kind of an elliptic PDE, we have control on the gradient. So you can think of this as some kind of a reverse Poincaré inequality. Remember, Poincaré is L2 norm is controlled by gradient. Caccioppoli, because of information provided by the equation, you can control the gradient by the L2 norm. Okay, so we want to control this. It's controlled by the gradient. By Caccioppoli, you can control the gradient by the L2. So the question now here is, how do you control the L2 norm of the solutions? So the last term here can be roughly interpreted as how flat V is, because this is just a constant function. So we can actually control that by, the arguments are technical, but roughly speaking, we can control that last term by additivity defects. And again, what is this? It is the strictness of sub-additivity from one scale to another, and the variance of the maximizers of the dual problem. So let's see. Let's go back. So controlling this term, we need the additivity defects, plus you need to control the variance of like gradients of the maximizers of the dual problem. And the arguments are a bit technical, but to get that, what you actually need to do is to use the independence assumption in a weak way, to show that the variance of the gradients of the maximizers would actually contract as you go to larger scales. So similar to what we have here, sorry, I'm backtracking a bit. Similar to what we mentioned here, we can actually show this for the variance of the gradients of the maximizers, that it contracts as you go to larger and larger scales, and you actually know how big or how small the contraction is. So once you have those, then you're done. Okay, so let's just recap. I'm sorry, I hope that this is not too dizzying. We want to control this because once you have this, you're done. Okay, so the control on this is given by J. Because of the properties of J and the assumptions on the random matrices, you can control J by this one. So now it boils down to controlling this. Controlling that is the complicated way where we use a mix of information from the equation and some other technical arguments. But with those in place, we have the following analog, quantitative analog of the homogenization result that we had before. So let's see. Let's just go there. So the result is this. So we had something similar. Let's just move to the final result. So again, we have here the random problem. We have here the homogenized problem. And the different thing here is we have a random variable here that we're calling chi s. And what this means, you can think of this as just its tail behavior is that it's more or less like a constant. So asymptotically, it's like a constant. So what we have is the error terms are controlled by data times multiplied to something that you know would go to zero. And in fact, you know how fast would go to zero. So you have epsilon here to this power times epsilon here to this power. Multiplied to a random variable, it's random, but asymptotically, it's just like a constant function. So in this sense, this is a true quantitative result. Now, there are plenty of questions after this, like, for example, is this result optimal? And what about correctors? And in fact, those questions are intertwined. To get the optimal estimates, you need to develop a theory of correctors. And very different from the periodic case, to develop the theory of correctors here, you need to look at like regularity of the problems that you're working on. And so if you're interested in that, I can give like a reference pointing to that. So that's it for my talk. I hope you got something from it. I guess if anyone has questions, I'll be happy to answer them.
Yes, thank you very much, Reggie, for that talk.
Yes.
I believe it's, what time is it there? Right
it's
now
11.
it's 11, it's almost 11 p.m. Okay, so thank you for taking the time. So the floor is open for, so first let us give our Yuji a round of virtual applause. Thank you.
Thank you.
Okay, so we are opening the floor for questions. So you may raise your hand, anyone. Okay, so Sir Ernie, you can posted some party emoji. Okay, so let me call on Mark.
Yes.
Sir Mark has a question. Yes, you can unmute yourself.
Hi, Ryuji. It's glad to meet you again.
Hello.
It's been a long time.
Yes. Yes.
Very nice
Good.
presentation, by the way. I loved
Oh,
it.
thank you.
I was just I was quite interested with how you connected the the normal periodicity with the concept of randomness. And I was just curious, when you were doing the scales again, what you assumed some sort of sub-additivity, right?
You can prove that you have subadditivity.
You
So
can prove.
yes, you can prove that the energy. So you have the energy in a domain. So it sort of kind of acts like some kind of a measure or something, like given a set U, it would spit out like a number, a positive number. So you can show that that is subadditive.
Okay.
Uh-huh.
For us to be able to prove that sub-additivity, we assumed two things, right? And for us to be able to do that, what we did was that when we somewhat partitioned our space, there is some sort of independence, if I'm not mistaken.
Uh-huh. Uh-huh. Um, okay. Mm-hmm.
Okay. But eventually, what we're doing is that we are cutting. We're going to be studying on different skills. So I was wondering, is that is that okay? I
So
sorry.
I don't have the exact proofs like memorizing off the top of my head, but I think to show subadditivity, I'm not sure if you need independence. The subadditivity would come from the fact that mu's are defined, for example, mu's are defined as an infimum. So there is some kind of a standard argument that, okay, since it's the minimum energy, if we consider problems in a sort of you patch solutions, so you form a partition. You form a partition of your domain. In each of those like subset, you have different solutions. You glue them together because of the definition of mu as an infimum. You get that it's the energy given by the solution to the full problem is going to be less than or equal to the energy of these sort of glued things. So that works from you. For J, it's a bit different because the way that define that we define J is a bit different, but the idea is sort of like the same. We're sort of leaning into that you take a partition and then you look at solutions to some problem in each of these subsets, you glue them together, and then you compare, okay, so what's the energy for like the original thing where I didn't do the gluing, and what would be like the average energy for this glued thing?
Okay. Okay. For my last question, uh, okay, my last question was lost. I was lost as it. Okay. When you do the partition, well, at least in this presentation, I think you did some. Uh, my question is that is there such a thing as a best partition? Well, I'm thinking now on the idea of optimality, where what we did here is that you uh if my understanding is correct, is that you have a sort of a space, and then you basically tiled your space. And so well, there are different types of tiling. So my question was that maybe this isn't a crystallographic question, but is
Oh,
is the square tiling the best tiling for it, or does it matter? It does not actually matter.
I am not sure if it's gonna matter because I am not sure like how things would be different if you consider the different tiling. What I know is that the sort of way that we partition things, we're just using cubes because it's easy to work with cubes. Like
uh,
yes, so
yeah.
that's the main. It's easy to think like okay, if because note that you are working with d-dimensional problems, so if it cubes are very nice. For example, in R3, you can think of like cubes in R3. But if you look at something more exotic, it might be difficult to think that, okay, I'm guaranteed you, because at some point you need to count. For example, think of a cube in R3. Um, you and let's say you partition it into like 27 subcubes, you sort of need to count like how many like neighboring subcubes would each cube have. And if you have like more exotic partitions, it might be more difficult to count. So I don't know what the payoff would be, but what I do know is working with cubes is nice and easy. Yes.
So thank you, Mark, for your questions. Do you have any additional questions, Mark, or was that the last one?
Oh, sorry, actually, I was cut off.
Okay, sorry. Okay, so Yuji, speaking of the tilings, I think you mentioned that you chose to have, how do you call it, triadic partition instead of a dyadic one. Sorry, let's recall again, what again was the advantage of partitioning it that way instead of having a dyadic one?
We can draw it. Okay. Oops.
I'm sorry, I was cut off. But that's my gosh. I was just quite interested with that. Thank you, Ryuji.
Yes, you're welcome. So with regards to Sir Gino's talk, okay, so if harmonic analysts would usually work with dyadic decomposition. So for example, if you have a cube and you work with dyadic decompositions and you decompose it with the cube of like just the previous scale, you'll get this, something like this. Now, it would be useful for us if we have things that don't touch each other. So in this case, this touches this, and it actually touches everything. If we work with triadic cubes, then this is far away from this. So it's a matter of convenience. So I think it would be possible to work with dyadic cubes, but the book that I'm studying work with this because it's easier to work with. So again, similar to Mark's question, it's nice and easy.
Okay, thank you. Do we have other questions from the panel, from the audience? Yes, sir, Ernie.
Hi, Gino. Hi, Ryuji. Thank you very much for this talk.
Thank you, Potter.
Tanong lang, you considered in the second part of your talk, you considered a problem with the Neumann boundary condition, right? And in the first problem, in the first half of the talk, you showed us a problem with Dirichlet boundary conditions, and you said that there was that function omega, which tends to zero, but we didn't know how fast exactly, how fast it tended to zero. So sorry if this is a basic question, but is it possible to also apply the techniques that you showed us in the second half of the talk to the earlier problem, so that we get a clearer estimate, a true quantitative estimate of how fast the thing tends to zero?
Okay. So to answer that, we're using the Neumann problem as a tool. So we're not getting estimates for how fast the convergence is for the Neumann problem. So the results that we have are we're still looking at solutions to a Dirichlet problem.
Okay. Sorry. Thank you.
We're using the fact that the Dirichlet and Neumann problems are going to be closer to being dual problems to each other at larger and larger scales. So to get this, so to answer that question, we're using the Neumann problem as a tool. So we're leveraging the information we gain from at larger scales, that these two problems are closer to being dual, and that gives us control on the error terms.
Okay, thank you. One follow-up question. You introduced this notation, that curly O, and then you had e to it's a negative exponential, of t to the s, which which I found interesting, because normally you have a negative exponential, but you still raise t to the power s. Was there any significance of using the t to the s? Will it not work if you only have t to the first power? Here, yes, precisely here.
I think the authors were just being general about it. So here, what we actually have is S is equal to 1.
Okay.
And
All right.
with regards to um, optimality of this, I think this is optimal. For example, you get this exact exponential sort of decay in the random checkerboard example, so it's sharp. But I guess with regards to your question about like this notation, people working maybe in probability theory kind of wanted to have something general,
Just
so
for
they introduced
generality, but
this S.
in your
Yes,
own in your example, S equals 1 is
yes,
okay. Is good enough.
S equals 1.
All right.
Yes,
Thank you. Thank you. That's all.
yes, Professor. Thank you.
Okay, thank you, Sir Ernie. Do we have other questions from the audience? Okay, so if none, let us give Yuji another round of virtual applause. Yes, so thank you very much, Yuji, for that talk, and
Yes.
thank you
Thank
to
you for having
the
me.
audience. Yes.
Gino, before
Yes.
well, thank you again, Ryuji. But before we end, I'd like to mention that Ryuji is very much open to Ryuji and his friends, not just himself, no, very much open to conducting a series of webinars on topics related to this. And so those who are present here, I presume, are interested in PDEs. So if you could just send us an email if you're interested and if you have any preferred schedule. So we look forward to organizing this also face-to-face next year, but in preparation to a face-to-face workshop or seminar, we think that it would be good to have a series of webinars so that we can already discuss, or Ryuji can already discuss the preparatory concepts, no, before we dive into the more interesting ones. So thank you very much.
Okay. Yes. Thank you. Yes, we can. I think we can work something out in that sense. Okay, so thanks. Question. Okay. So again, thank you, Ryuji, for giving the talk, and thank you to the audience. So our next webinar will be on April 19, where we'll be hearing from the discrete geometry and combinatorics group. Okay, so until then, goodbye. I will see you again in 2 weeks.
Thank you, everyone. Have a good day.
Thank you.
Good night.
Goodbye.
Bye, Ryuji.
Bye, Ryuji. Good to see you.
Good to see you din po. Good to see everyone.
Bye.
So thanks again. I will end the session now. Okay, goodbye.
Thank you, Gino.
Salamat po.
Bye.